my co-author is Russell Smythe, Monash University, and I hold few positions in different places. Okay. Okay, I use this one. I'm okay. Okay, let me talk about a little bit of motivation. Well, the content. I'm going to talk a little bit introduction of critical minerals. That is the part that you're going to teach me more than, but anyway. And then we have a theory called the back-end risk premium. And that's basically explain why the investment into critical minerals doesn't flow as expected, given the higher prices that you experienced in 2022. So basically, we're going to use some insight from earth science. We do a financial interpretation and then an economic theory. And then we're going to talk about how artificial intelligence potentially can solve this issue of the lack of investment in critical minerals. Let's just put it all together. Okay, one of the why a macroeconomist is studying critical minerals in Australia, I'm going to make it quite obvious with the first sentence. According with the International Energy Agency, $100 trillion have to be spent in clean energy transition over the next 25 years. And that is the largest macroeconomic shock in human history. Okay, we never have such a global macro shock. Okay, so that's why it's so important. And unlike the energy sources of oil, coal, gas, the one that we use, clean energy production requires an unprecedented amount of critical minerals, such as copper, lithium, nickel, zinc, cobalt, rare earths. But the critical mineral list, according to US, there are 50. Consequently, the supply shortage of critical minerals that is needed for achieve global net zero target has gained significant attention, as you know, and the International Energy Agency basically is saying that the investment need is half the investment expected for critical minerals is half what we need to achieve net zero, or two different scenarios. They have actually, the International Energy Agency have a sustainable scenario, which is net zero to 2050, and another scenario which is stated now, which is not consistent with 2050, but the focus is 2050 or 2060 is not going to change much the presentation and this idea. Okay. Well, this I present that for economists more than for you guys, but the obvious steps and SDS, those are the steps is the stated scenario, policy scenario, what international energy consider, and the sustainable is the one that is consistent with net zero. And as you can see, the number of only in the top 5, we need to ramp up significantly the amount of critical minerals to make it possible. Here we can see the latest list of critical minerals, and important to understand how we define critical minerals is supply risk in the horizontal axis and in the vertical important to energy. And the latest one show that, in the top, lithium, nickel, cobalt those are the ones that they are more critical in terms of these two parameters. Interestingly, this list changes significantly every year and things move around, but in general, not much. In general, all these critical minerals always are there, moving a little bit from one place. Now, here is what it caught my attention, which is that basically what is called the back-end risk in project development. There was a few papers wrote by these co-authors in Western Australia that basically show that the investment, it shows that what is called the back-end risk, which actually means that some projects, development in mining, investors attribute just too little value at the beginning compared to others in which, for example, oil and coal and iron ore, in the first few years of the project, already the market attribute like something like 80% of the value. So investment flow quite quick because there are not much risk, or the risks are much lower than with some critical minerals, which are called back-end risk, because the risk is at the end of the project. And I'm going to make it a little bit more clear. But also, I found it, we work with technical risk and not technical risk. You will be very familiar with that. But technical risks include equipment failure, geological uncertainty, resources estimation inaccuracy, etc. And non-technical risks are much more related to the politics, the political stability, environment regulation, etc. I always, as an example of that, is what happened with cobalt, where 50% of the global proven reserves are in Congo. And that is challenging because it's very hard to invest in Congo. So that's basically show that. Now, here is where I explain this idea of the back-end risk or front-end risk. If we look at in the vertical axis, we have the value of the project. In the horizontal axis, in the horizontal axis, time. And in the blue line, you have what is called back-end minerals. And in the red, you have what is called the front-end mineral. What that means is, and this comes from the paper of, or the multiple papers that these authors did in science. And that basically shows you the value of the project given the time of the project development. For example, in the red line, you can see that many of these, I'm going to generalize a little bit, but basically show that if, for example, in iron ore projects, which is called a front-end mineral, the investors attribute value, much more value from the beginning. Okay. However, what is a back-end minerals or back-end risk, then the value is attributed at the end of the project. What that means is basically is that you don't get investment, right? That's sort of that is, the interpretation. Keep in mind that according to the International Energy Agency, and taking a little bit of the data for the last 30 years, between start exploration and collect and actually produce, it to take 12.5 years in average. So you can see that in a world with many uncertainties, it's already hard to get investment thinking 12 years ahead because technological progress, changing policies, etc. But it's particularly bad if the investors don't attribute enough value from the beginning. Okay, so that in finance is quite, I mean, what it made me think about that initially when I see that, I already automatically think about what we call it premiums, right? Premium risk, for example, liquidity premium is, it's a theory, it's a Nobel Prize theory in finance, which basically show why you have the required rate of return of investors is higher from when you have an additional risk, basically. So with that in mind, we explain that in this way. Suppose that, by the way, F stands for this is the required rate of return. So basically, this is a very well-known concept in finance, where how much investors expect to actually invest in any project, right? And of course, it's a function of risk. So if assuming that the front-end minerals, and as an example of those and described by the authors on Earth Science, generally are iron ore, coal, oil, and another more, the sources that we use, you know, that power 85% of the global economy. So a premium can be seen in this way, is that this is the required rate of return of investor for the resources that we know more, and the risk, the backend risk is on top. So, and this is the from T1 to T2 is the development of the project. Okay, so that basically means that there is an additional rate of return or an additional premium that investors require to invest in critical minerals. Broadly defined, you're going to find out that then when we go critical mineral by critical minerals, some of them have this premium, some of them they don't. Okay, but this interpretation is quite important just to try to understand and measure this additional risk. Okay, because so far, if anyone wants to invest in, I don't know, lithium, what is expected rate of return? No idea. So that uncertainty generally put actually the rate of return even higher, because uncertainty is one of the big issues for investors. So this is just to show you. Now, I know that you say, well, but this line is not necessarily straight, okay? And we don't know exactly the shape. But what we know is that at the beginning, the risk is higher. And as soon as the project keep advancing until they start extracting, and when we start when actually the extraction starts, or when the process starts, the risk disappears because you don't have the risk of the government to stop the project, or it's much lower than during the project development. Okay. And actually, in the previous, here you can see that here you have, you know, all the stage: exploration, scoping, feasibility, development, mining, and basically the back-end risk premium, or the back-end minerals generally after develop. This is the time when the investors start to attribute value, okay? Because this is too risky at this stage. And once again, is different for each critical mineral. So, but that is what we are working later on. Now, so how we consider how can we evaluate each critical minerals in terms of risk? So what we did here is that we look at the two aspects of back-end risk premium: technical risk and non-technical risk. That is established for you guys. And technical risk was already measured, so then I'm going to show you how to estimate. But the non-technical risk, that was the challenge in this paper. How I measure non-technical risk for each critical mineral. So we here use a little bit of economic theory and a simple index, and my co-author, Russell, that it will be somewhere online. That was in the first part. We sent the paper for to journal, and then just tell us, yeah, well, but tell us more about how to estimate non-technical risk. So, first of all, if we look at the long term, we look at the proven reserves, right? Because that is, for example, if let's just come back to the case of cobalt. The non-technical risk of cobalt is clearly high because 50% of the proven reserves are in Congo, and in Congo it's very hard to mine and invest. So the data of proven reserves, we take it from the US Geological Survey, which is not necessarily very accurate because sometimes you can see that the numbers are quite rounded, but at least is the source that we trust more. But a lot of more have to be done on this space to map well. So if we map proven reserve better, we're going to have better measures of a non-technical risk premiums too. But as And then my co-author Russell said, well, how we look about investment risk? And we couldn't find something on internet, and he went to the library, find a book, and they found the Fraser Institute annual survey of mining, which is where they produce an attractive investment index, where they ask companies in different countries, they've been doing that for 10 years, how attractive is invest according to different criteria, environmental regulations, government taxation, etc. So if we wait, we figured out that if we wait, if we have the proven reserves weighted by the investment attractive index for each critical mineral, okay, that is going to give us an idea how, an idea of no technical risk, basically. That is going to be, I'm going to make it much more clear soon. So, if we consider that, and what we call it not technical risk premium, how we move from here, which is just multiplying the per mineral, we multiply the proven reserves times the risk of the country, and then we add it all, okay? And how we move to, and what is that no technical risk premium? Well, it's just we define the premium compared to the non-critical minerals, which have lower technical risk, and we make an index on that, basically looking at the technical, non-technical risk of the 4 largest, let's just, on iron ore, coal, and oil. So the one that we consider that they are front-end risk. And basically, by having this index, we estimate the percentage change of the non-technical risk of this benchmark compared to each particular critical mineral. Okay, so the difference on that is going to give us what is a non-technical risk premium, which is the additional risk premium over this benchmark. Okay, because at the end of the day, we know much more about the risk in an investment in coal, oil, and iron ore, but we know less about the emerging critical minerals. So here is how we think about it. First of all, we create a non-technical risk index of minerals. Now, we did it for 90% of the value of the critical minerals. There are not all the critical minerals here because many of them, the proven reserves are not there. The data is not there. So what you can see here is our benchmark, which is no critical minerals, is 64.25. And then we have the score for all the others, rare earth, platinum, all the critical minerals. Once again, this is roughly 90% of the value of all critical minerals. So the others don't exist, basically. So the data doesn't exist. So and with the formula that we showed you before, we calculate the premium. Okay, so basically it's going to be the difference between that benchmark and each critical mineral. So, for example, the mineral with largest non-technical risk premium is rare earths, which actually means that which is 30.6%. Basically, what this tells you is that the requirement rate of return for investors should be 30.6% higher due to non-technical risk compared to the benchmark. So this gives already some information to investors. Okay, and this is only the non-technical. So when we look at then we did the same with the technical risk. The technical risk, this is a little bit different how we estimate. In this one, we simple work with the paper of Skype, guys, to 2016, which actually he measured the technical risk of 49 minerals. So we did the same here in terms of looking at the benchmark okay? And then look at the percentage change compared to each individual critical minerals. In this one, we already take the index that they have. Let's just talk a little bit how they did it, and you will be the judge about if this paper estimates well. But basically, this paper estimates this technical risk using 6 criteria: crustal abundance, crustal concentration, easy of mining, and easy to processing, critical use, and diversity of use. So the index is not very fine-tuned in the sense that use values 0, 0.5, 1, etc. So our non-technical, the one that we estimate is much more precise because you have it's not a rounding. But this guy did that. So once again, we look at the benchmark of the other minerals, which is the TR, I mean the technical risk of non-critical minerals, minus minus the technical risk of critical minerals. So the C star for critical minerals. Now, once again, then when this is not for all the critical minerals, then we go one by one. So that's why we have the that's why the C stays for critical minerals and the NC star stays for the non-critical minerals. So here we have the equivalent, but with technical risk. So the non-critical minerals have a score of 3.5. That is the average of these 3. And then we have the value of the 14 in that case. That's once again data availability. But that's basically show you some interesting things. For example, copper and antimony have actually higher score than non-critical minerals. It means that copper, in terms of technical risk, copper is easier to mine than the benchmark. So once again, what matters here is the premium from economic perspective. So you can see that tin have a 50.7, 57.1 additional risk premium than the benchmark over. But for example, bauxite and copper actually have a lower than the non-critical. So that will give us an answer. But at the end of the day, what is the back risk and premium is the sum of the non-technical and the technical risk. So here is what we add forward. Let's start by the 10. 10 basically tell us that the rare earths, for example, have both positive technical and not technical risk premium. Actually, it just, I mean, the number is not there, but it's roughly 70%. So the required rate of return for investors has to be compared to the non-critical mineral, has to be 70% higher. Okay? So that is a good information for investors because now they know why they have to pay more and how much they have to ask for that return. And then you have for others, copper is one of those that actually, there are not much premium over others. Okay, and in figure 9, we just create a scale 0 to 1, and with non-technical risk on the top, technical risk, in the vertical axis, and in the horizontal axis, technical risk. The black line is the non-critical minerals benchmark. So you can look at the distance between the benchmark and each of these important critical minerals. Rare earths is on the roof. It's very high non-technical risk and high technical risk. Tin, for example, is very high in technical risk and not very high in non-technical risk. But what does tell you by looking at this chart is that most of the critical minerals, in particular the largest one, have much more risk than the non-critical front-end minerals. And this is quite informative for investors, as you know, because now we can think about that. Now, an important aspect is that technical and non-technical risk are time varying, okay? Because when we discover more reserves, this value should change, right? And when technology advances, also will change the technical one. I always give the example of the lithium in Chile. Because I'm South American, but also because it's a good example. Chile have lithium in the in a very dry place in the what is the desert of the Atacama Desert. That's exactly right. So that brings a lot of technical issues because they don't have water, but then also non-technical issues because the farmers are complaining because they don't have water and they use the water for mining. So technical and not technical risk, they're supposed to interact, but also they're supposed to change over time because of the technical advances. Use, for example, technical risk can be reduced by manage better the water. So, or use less water given the technological advances. And non-technical risk will change when we discover new proven reserves in different places, which can go one way or another. Actually, in the second paper, we are working already. We have the non-technical risk premium for the last 10 years. Not for this paper, but and it's interesting how much changed. And it's actually quite interesting because since 2021, when the lithium prices went to the roof, what happened is that countries like Chile, they nationalized. So the risk increased and the non-technical risk increased too. So we have this delay, this problem, which is going to actually slow down energy transition, is that the countries that have critical mineral, when prices go up, they just put more regulations, they just higher taxes, and even nationalize, like Chile did, or Bolivia, similar thing with lithium. So this is quite interesting because in the energy transition policies, that global policies, we never consider this point, that when prices go up, because, for example, we know that the Inflation Act of US is going to invest $450 billion in the supply side of critical minerals. Basically, they are encouraging electric vehicles, and that increases the demand for critical minerals. But on the other side, you have the countries that have the critical minerals that they say, okay, prices increase, the government try to get more of it, not necessarily for the society, but they're trying to get more revenue, so nationalize or increase taxation. Actually, what happened in Congo is quite impressive in terms of how the non-technical risk increase, because they increase the taxation, the royalties significantly. So this is a very problematic thing for an energy transition, which is quite inconsistent, because the rich countries that actually are putting a lot of money for energy transition, they increase demand for critical minerals, but the one that supply the critical minerals increase the non-technical risk by saying, hey, yes, fine, we are into energy transition, but, you know, let's get more money for the government. So this is what is quite challenging, and it's going to come up in our next paper. Now, how much is the shortage in investment on critical minerals? Or in other words, how much is the back-end risk premium, which is this additional risk weighted by critical mineral, but specific critical mineral? Well, that is roughly, according to our estimation, we look at what is the average weight, the WACC, which is the weight average cost of capital for the we survey more than almost 2,000 companies that produce non-critical minerals. And basically, we weight each of these critical minerals premiums, okay, according to the value, the market value, by two different scenarios. The scenario of the sustainable scenario and the state energy scenario. So, as you can see, it's not much difference because the only thing that these scenarios change is the weight expected for each mineral. So this is provided by the international negotiations. So in other words, from 2023 to 2035, there is a shortage in investment of around $700 billion, which is quite complex because, as we see before, why you're going to invest in Congo if there are, if they keep increasing taxation and also there are also other risks associated with it. So this gives us the first idea of why energy transition is not going to happen if we don't have $700 additional billion invested in critical minerals. And that had to happen in very particular places. Australia is one of them. Australia, according to our estimation, Australia have 20% of the global reserve, proven reserve of critical minerals, with a population of 0.3% of global GDP, which is roughly $700,000 per capita. It's not, and if we consider all the resources, it is 1.3 million per capita. Not per adult, per capita. So Australia is actually the richest country on earth. Since we try to move to energy transition, this idea that coal is going away and that's a problem, well, we are richer than before per capita. But governments here or in Congo, in other places where, I mean, let's be clear, between Congo, Australia, and the triangle of lithium in South America, we get roughly 50% of the global supply of critical minerals. Then there are pockets everywhere, and we will find more everywhere. But all these countries are quite, with the exception of Australia, the other countries are places where investors are reluctant to invest. And Australia is not getting better, so either in that sense. Then we talk about that. So, okay. Now let's just move to how artificial intelligence is going to solve some of the issues or reduce this risk premium. This is something that you know more than me, but by looking at the literature, there are many ways in which risk of mining in project development are improving all the time. Not everywhere, okay? In Indonesia, the issue of nickel is quite bad because they are extracting nickel in a very unsustainable way, which actually defeats the purpose of energy transition altogether, which is one of the big problems that happen here. But here we have a list of all the things that artificial intelligence potential can contribute to reduce what we call the back-end risk premium, which is the technical risk. Now I'm going to show you the economics of that. The economics of that is quite simple. We have what is called the well-known possibility frontier, production possibility frontier, which is this black line. Well, it's a mix between labor and capital. Okay, we have labor and capital, and this is the maximum that you can produce. Now, artificial intelligence, which is a capital intensive, so that's why it's in this vertical axis. Have the potential to increase production, right? Because we increase productivity. But the back-end risk premium is pushing that down. Why? It's because you don't have enough investment. So this is basically the economic interpretation of what is the potential of artificial intelligence and also the back-end risk premium that is pushing that down. So it's a risk for that. Now I'm going to read a little bit more precise. Well, this is this is basically showing you how artificial intelligence, by increasing artificial intelligence, can affect two aspects. One is the duration of the project. So if you shorten the duration of the project, your risk premium is lower. Okay, but also can reduce the risk. How reduce the risk? Well, if you, for example, in the environmental risk can be reduced by better mapping, safer practices, etc. And artificial intelligence can show many applications on that. But more exactly, and this is basically what it shows, there is a 50%. This is a simulation, right? Just to show the theory. That, you know, if there is a 50% improvement in terms of the risk of mining critical minerals, you know, the artificial intelligence can take $350 million on that back-end risk premium. And similar when we look about the shorten the period of time. And that I'm going to just formalize that a little bit. Oh, no, where is this? This one, sorry. I think I skipped this one. Sorry about that. This is much more clear, the situation. You remember the original figure that I showed you, the risk premium? Altogether, well, if the risk premium is from RF to RB, okay, altogether, if you reduce the risk, you are reducing this premium, okay, in this way, by reducing the premium by itself. And if you reduce the time of the project, you are reducing it by doing this. So you are reducing, in other words, if we can, if rather than in average, this project takes 12.5 years, it takes 6 years, okay, the risk is reduced significantly. Okay, because risk is a function, financial risk is a function of time and risk. So that is what it shows. And, you know, estimating that is quite easy once you know how much improvement in artificial intelligence is reducing this project. And that's why I'm trying to work with Geoscience Australia, because they can give me this data to do a serious econometric work. So the part of the artificial intelligence is theoretical. Okay, you know, I don't have estimations on that. We need data, but at least give us an idea how artificial intelligence can reduce this risk premium, and companies have data to evaluate that. I mean, we can look at different projects and how over the years some improvements in artificial intelligence can reduce it, reduce the time, and reduce the risk. So I'm going to go for some conclusions and then a little bit of Australia. In our opinion, the biggest impediment of global decarbonization is the supply of critical minerals, okay? Because we are all the governments around the world invest in clean energy production, but if you don't have the supply of critical minerals, then you cannot achieve the order. So, or potentially, what happened in 2022, price of lithium increased 700% in 2022, okay? So it increased so much that at that price, clean energy production is very expensive, and then you're going to start population saying, no, I'm not going to pay for it, okay? Or the governments have to invest too much. So we developed this sort of 3 new concepts. One is the back risk premium, which is the additional required rate of return that investors need for each critical mineral. And not all critical minerals are alike, of course. But also we divide this, or we decompose in 2 things, in non-technical risk premium and technical risk premium. So, and the potential in the future to look at the interaction of these 2. Because as I mentioned before with the Atacama Desert, if you improve the water supply, this is technical, improving the technical risk, but also you may improve the relationship with farmers because you are using less water. So non-technical risk. And then But here, now, here is the problem, and here is what we suggest in terms of policy. In terms of policy, we look at the global decarbonization, we believe that is wrong. We believe that the only way for energy transition to happen at reasonable prices, because if prices increase, then people will oppose and vote for governments that give you lower prices of energy, is for the International Monetary Fund and the World Bank to invest directly in critical minerals. Why them? Why them? So first of all, because it's in the mandate, in the new mandate. But secondly, because you have to figure out how to invest on those countries, and the private sector won't do it. So they have to be a global institution that actually provide that investment. And the reason, and also what they can do on the process, because if the World Bank and the IMF also provide guidelines to governments on how to have a reasonable economic environment for investment in general. Those are the institutions that can reduce the risk by going to the Republic of Congo, South America, and just to say, well, if this investment come here to realize the energy transition, those are some policies that could also increase and bring the private sector into. So, by the way, $700 billion for the IMF is nothing. Let's just be clear. For the World Bank, it's just irrelevant, and that will enhance, and that will give the first minimum step to achieve energy transition, because no critical minerals with the current technology, not energy transition. And that's applied for secondary mining. So, implication for Australia. Well, in another paper that we published in 2024, we show that Australia has $15 trillion of critical minerals, which is crucial for energy transition. This is equivalent to 15 times the Australian total GDP. So that is, it's huge. I mean, I talk with politicians, they just don't understand the dimensions, but it's important. Australia have 20% of the proven reserve of critical minerals and a population of 0.3%. So we have to do more. And actually, in the paper on 2024, we argue why we are looking at trying to decarbonize Australia with a population of 0.3%. We will never, by decarbonizing Australia, we will never contribute to the global decarbonization. How we can contribute is by producing critical minerals, because that will reduce the cost of clean energy globally, okay? And that is a much larger contribution than a move to AVs here in Australia. Why? Well, because population of 0.3%, we are insignificant in terms of that. So while the government keeps saying, let's just, let's just invest in clean energy, which is fine. I'm not opposed to that. But what I'm saying is that, hey, what about if we just try to produce more critical minerals and then enable the global energy transition? Okay. And I haven't even talked about secondary mining, which is in another paper as I showed to you. But artificial intelligence also in secondary mining, it could be, not only a historical economic opportunity for Australia, but also a historical opportunity for sustainable growth. And to finish, I'm going to say that one of the problems there is that we are looking the global decarbonization as how much each country decarbonize. But for example, if you produce critical mineral, you increase your CO2 emission. So, hey, critical minerals is good to enhance energy transition, but then you penalize me with CO2. So that discussion has to be, and that's why in the next paper we are proposing that the role of each country in energy transition has to be different. It has to be. Well, then I will provide in the presentation, but here we have a little bit of the proven reserves per country as percentage of global reserves. This is in the paper, so if it's too small, it's in the paper, don't worry. And then we have here the investment attractive index of the Fraser Institute, which is quite important to understand the risk premium. For example, here, this is the one, the latest one. For example, here you can see that Congo have a score of 48, which is very low compared to Australia that is 73. That's basically showing you how little attractive is, some countries are in terms of investment, because this is the investment attractive index. So this is what we use to construct with proven reserves the non-technical risk. But this data is quite important, and hopefully the Fraser Institute or someone else can provide much detail in the future, because this is a survey done for the last 10 years, but still the sample quite small. Thank you very much.
Thank you very much, Joaquin. It was very interesting. Do we have any questions from the audience?
Thank you. Well, my name is Nana Georgievich from Brandon, Australia. Just kind of small thing. When you compare copper is you consider critical minerals, which is a critical minerals, and you calculated your risk premium for copper compared to the non-critical minerals, such as, for example, iron ore. And in your calculation, it's a negative, meaning it's easier to mine copper than iron ore. Is this what you're saying?
Is that, well, not exactly. It means that the risk of investing, the required rate of return of an investor, the investor says, oh, I'm going to invest. I can invest in coal or iron, or copper or iron ore, okay, or whatever. So it's just saying that the risk, they should ask for not much return that from iron ore, for example.
Maybe I should add,
yeah.
Your calculation refers to technical risk of copper versus iron ore.
You're talking about technical risk.
Yes. And,
okay. Yes.
And it's negative.
Yes.
Which is, my understanding, it's a bit kind of strange.
It's strange. Okay.
Because in case of copper, for example, we are looking to recover as a copper concentrate, typically 0.5% of the mined ore, 0.5% of the volume of the ore. In the case of iron ore in Western Australia, we are selling about 80% what we mine. 80% versus 0.5. So obviously, technical risk for copper is much, much, much higher.
Okay, that's okay. Let's just go back to. Now I have to defend another author, but technical here. No, let's go.
This graph is
yes, here. No, but the technical. Okay, no. No. I understand. This is what clearly what I showed. Now, I am not saying this is the first attempt to measure risk, and I am relying 100% on the work of 2016, which evaluate these 6 characteristics. This is the best that we can do given the literature, but there is a lot to work on it. So what we provide here is like a general framework now with more data, and hopefully, and also with criticisms about, because these 6 criteria that they use, I mean, I'm not sure if this is the best way to do it, but that is the only way, or the only paper that we find in the literature that attempt to measure technical risk. Guys, you have to do a lot of more technical and non-technical risk, and that will help a lot of investment. So in both, in technical and non-technical risk, this approach is the best that we can do with available data. But with artificial intelligence, we can do much more to measure better. So you could be perfectly right, and you know, and this author wrong in this estimation. But it's very good that we open this discussion, because if you guys try to measure very technical risk and non-technical risk, both by mapping, by understanding the procedure better, etc., we can provide more accurate estimation of the premium, and that is what investors need. Because this idea that you're going to invest in a project without understanding any risk, okay, is crazy, basically. And that's trigger more uncertainty, and what is uncertainty? More risk, and more when you invest in something that have more uncertainty, you increase the risk, right? Because you not increase the risk, you increase the required rate of return. You're asking for much more to cover yourself for that. But thank you very much for tell us, you know, more about that. Yeah, that was a great point.
Okay, thank you. Then we have we have a question online. He's going to ask it.
Thank you, Christy. Greetings from Tasmania, Professor Vespignani. Yeah, it's very cold down here. We're very jealous that you're up in the lovely warm state of Queensland. Of course, very interested in the back-end risk premium. I'm Dan Dorgard, just in case you can't pick up my my voice, Joaquin.
No, we hear very well.
Okay, so it's just in regard to this concern about getting companies willing to invest in critical minerals. And I'm just wondering about the extent of the potential for diversifying the risk between critical minerals and non-critical minerals, or front-end minerals, particularly with respect to the possibility of moving infrastructure over if the certainty becomes, well, if the risk become more certain. And the reason why I'm asking is maybe there's greater attraction or potential for diversified miners to consider expanding investment into critical minerals rather than, for example, standalone separate companies. Any thoughts?
Well, many companies are doing that somehow. I mean, BHP, we can see that they are entering the new market. Now, an interesting thing that is not well developed yet, and for finance guys like Dan, is that we haven't explored much the hedging of this risk. For example, if you have a portfolio, well, first of all, now there is not enough financial instrument to hedge risk in these critical minerals. When you hedge, meaning that you are actually have the opportunity to cover yourself for the risk, basically, is not well developed yet, but is critical to hedge the risk. And already companies like BHP, they are trying to hedge in one and with the other automatically by investing in non-critical minerals and critical minerals at the same time. So, but the financial market on that is quite behind. So, I mean, hedge oil is very simple, right? I mean, if you just can buy a contract of oil that's 2 months ahead, 3 months ahead, 5 years ahead. So I can buy oil at, I don't know, $75 a barrel 5 years ahead. So with that, you hedge the risk, okay? However, the critical minerals market, yet in particular, because in some particular are not big enough, and also have the problem that the market are segmented. Oil prices are basically the same all over the world. Yeah, with some difference, but they move together. But for example, for lithium, there are 6 different prices in the world. The market is not integrated. If the market is not integrated, you are adding additional problems because the market is not efficient. Okay. The last presentation that I here in Eria basically show that the lithium prices, depending on the location, change significantly and they don't move together. So what you need for economic efficiency is to integrate the market, like happened with oil and well, with the I mean when the market becomes bigger, naturally they integrate because you know, if Australia don't want to pay for oil this amount, you sell it somewhere else. But with lithium, it's more complicated, and part of the complication, and also this is something that you guys probably could work on, yeah, proposing projects, but is that the oil, for example, or coal is different in the sense that compared to, for example, lithium, because lithium is not what you put in your car, okay? Lithium is what the manufacturer put in your car. So, you know, oil is directly to the consumer somehow, and the critical minerals are not. For example, copper is in the grid, right? And that is, you need the government to invest on that. So, a very exciting, Dan, thank you for that, because that is a very exciting thing that we can do in finance, which is just to start to hedging, to have products that hedge critical minerals. And so if you are a company, you can hedge, you can, you know, say, okay, although my operation is only in lithium, I can buy contracts of other minerals to hedge the risk in case lithium is substituted by coal. Okay, so, yeah.
Thank you for that. Yeah, I hadn't seen the scope for innovative derivative products, just like there are with the other underlying fundamentals like oil. That's quite exciting for the future. Do enjoy the warmth there. It's going to snow here tomorrow. Just heads up for your return.
Okay, thank you.
Okay, thank you very much. Unfortunately, we have run out of time. So for all there are some more online questions, but they can just reach out to you
Yes.
afterwards via email or something. But thank you very much for everyone being here. Next week, we're not going to have a presentation. The next seminar will only be on the 26th of July because there's a semester break at the moment. So yeah, I hope to see you all there. And thank you once again, Joaquin. It was very interesting. And please, everyone, join us for some tea and biscuits afterwards.